Welcome to this tutorial on game development using Godot 4.3. Today, we'll be walking through the process of creating a Flappy Bird-style game using the Pastebin art pack from Kenny.nl. This tutorial is designed to be concise yet thorough, giving you the essential steps to get your game up and running quickly. We've included links to the project code and the Pastebin art pack in the video description. Make sure to download them before getting started so you can follow along seamlessly. Let's begin by opening Godot 4.3 and creating a new project. Click on New Project and choose a location on your system. Name the project Pastebin or something similar. Then click Create and Edit to open your new project. Once the project is open, we'll start by creating our player. Begin by adding a node 2D, which will serve as the main player node. Rename this node to Player to keep things organized. Now, we'll add the player sprite. If you've downloaded the Pastebin art pack from Kenny.nl, all you need to do to add it into our project is drag the unzipped folder into the root directory of our project or into the file system window in the bottom left. To add the sprite, add a sprite node as a child of the player node. This sprite node will hold the visual representation of our player. With the sprite node selected, locate the plane sprite in the file system. Drag the plane sprite onto the texture field in the inspector. You'll notice it's a little blurry. We need to adjust the filtering in the project settings. Open up the project settings, scroll down to the rendering section and click on textures. From there, change default texture filter from linear to nearest. Let's save our scene and start programming. With the player node selected, click on the Attach Script button in the top right corner of the editor. Player.gd is a good name for this script. Let's start by removing everything here except the first line. Let's start by declaring three key variables that will control our player's movement. First, we define gravity, which is set to 1000. This value will simulate the downward pull that continuously affects the player. Next, we have flap strength, set to -400, which controls the upward force applied when the player flaps. Remember, negative y values are up and positive are down. Finally, we declare motion, a vector that will store the player's current movement in both the x and y directions, initialized to 0. Now, let's define the process function. This function is called once per frame, which makes it the perfect place to handle continuous updates like movement. The delta parameter represents the time elapsed since the last frame, ensuring smooth and consistent motion regardless of the frame rate. Within the process function, we first apply gravity to our player's motion. By multiplying gravity by delta, we ensure that the downward force is applied smoothly over time, even if the frame rate changes. The line adds the gravity value to the player's vertical motion, simulating the effect of gravity pulling the player down. Next, we handle player input. We check if the UI accept action, which is automatically mapped to the spacebar, has just been pressed. If the player flaps, we set motion, to flap strength, which gives the player an upward thrust, counteracting gravity momentarily. Now we update the player's position based on the current motion. We multiply motion by delta to ensure smooth movement, then add it to the player's current position. This results in the player moving up or down depending on the motion value, which is affected by both gravity and the flap action. Let's save our script and see if this works so far. Press F6 to play this scene. While it's not placed where we will want it, we can see our flap action is working when we press space. Let's quickly create a main game scene so we can see a little more clearly. Create a new scene with the root as a node 2D. Place an instance of our player TSCN somewhere in the viewport. Rename this scene main and save it. Now press F5 to run it, and select current scene when requested. We can now see the plane movement mechanics working much more clearly. Now, let's take it a step further by adding rotation to give the plane a more dynamic feel. First, we'll declare two new variables. Max rotation angle is set to pi divided by 4, which gives us a maximum rotation of 45 degrees. This will control how much the plane can tilt up or down. Next, we have rotation speed, set to 5. This determines how quickly the plane rotates towards its target angle, giving a smooth, gradual tilting. Inside the process function, we calculate the target rotation based on the player's vertical motion. We divide motion by 1000 to scale the value appropriately, and then multiply it by max rotation angle. This gives us a rotation angle that increases as the player moves up or down, creating a natural tilting effect. Next, we use the lerp function to smoothly interpolate between the current rotation and the target rotation. The lerp function takes three parameters: the current rotation, the target rotation, and a value that determines the speed of interpolation. By multiplying rotation speed by delta, we ensure that the rotation speed remains consistent, regardless of the frame rate. Let's press F5 now and see how this looks in action. You can see the plane dips and rises as it climbs or falls, which makes it feel much more dynamic on the screen. Now that our player is set up, it's time to introduce obstacles. We'll start by creating a new scene specifically for the obstacles, which will challenge the player as they navigate through the game. Begin by creating a new scene. For this scene, we'll set the root node as an area 2D. This allows the obstacle to interact with other nodes, such as our player, by detecting collisions. Rename this node to obstacle to keep things organized. Next, let's add a sprite node as a child of the obstacle node. This sprite node will hold the visual representation of the obstacle. With the sprite node selected, locate the rock sprite in the file system. Drag it onto the texture field in the inspector. To make the obstacle interactive, we'll add a collision polygon 2D node as a child of the obstacle node. This node will define the collision boundaries for the obstacle, allowing it to detect interactions with the player. With the collision polygon 2D node selected, you'll need to manually trace the shape of the rock sprite. Click to create points around the edges of the sprite, forming a polygon that matches its shape. The rock object is a little bit too small here, so let's increase the scale on the transform on the area 2D node to 1.5. This will help make the game more challenging as we'll have more height to work with when spawning the obstacles. With the sprite and collision polygon 2D in place, our obstacle scene is now set up and ready to be used in the game. Save this scene as obstacle, TSCM, in your project folder. Next, we'll attach a script to the obstacle scene, which will handle its movement and interaction with the player during gameplay. Select Attach Script, and name it obstacle.gd. We'll start by writing the first stage of the script, which will handle the basic horizontal scrolling of the obstacle. Let's declare a variable called scroll speed, which is set to 200. This variable controls how fast the obstacle will move horizontally across the screen. Inside the process function, we adjust the obstacle's horizontal position by subtracting the product of scroll speed and delta from its current position. This line of code makes the obstacle move from right to left across the screen, simulating the effect of it scrolling toward the player. Now, let's enhance its behavior by introducing some randomness to its vertical position. To do this, we need to get the size of our obstacle and the size of the viewport. Then we can introduce some randomness to its vertical position. We start by getting a reference to the sprite node on our scene, as we'll need it to get the dimensions of the rock. You can drag the sprite in while holding Control. Next, we define the ready function. First, retrieve the size of the texture used in the sprite by calling getSize on the sprite's texture. We store this in the variable actual texture size. Then, we calculate half size, which is half of the texture's height. This will help us determine the range within which we can adjust the obstacle's vertical position. We initialize Godot's random number generator with randomize, which ensures that we get a different random value each time the game is run. We then use the randf range function to generate a random float value between negative half size and positive half size, storing it in the variable pipe height. This random value will adjust the obstacle's vertical position, making each obstacle appear at a different height. Finally, we set the obstacle's vertical position. By adding the pipe height value to the current viewport height, we position the obstacle somewhere within the vertical range of the screen. This ensures that each obstacle appears at a slightly different height, adding variety to the gameplay. With that done, now we'll add another level of complexity by adding a direction variable that will allow us to flip the obstacles, creating both top and bottom variants. We start by declaring a new variable called directionUp, which is a Boolean set to true by default. This variable will determine the direction in which the obstacle will appear and move. When directionUp is true, the obstacle will move upward, and when false, it will move downward. Inside the ready function, we now have a conditional statement that checks the value of directionUp. If directionUp is true, the obstacle will be positioned at the bottom of the screen with a random vertical offset, similar to what we did before. However, if directionUp is false, We scale the obstacle along the y-axis by setting scale y to -1.5. This flips the obstacle vertically, making it appear upside down. Additionally, we adjust the obstacle's vertical position to start from the top of the screen, again applying the random offset. This creates obstacles that approach the player from both directions, adding more complexity to the gameplay. The final part we'll add to the obstacle script for now is logic to remove obstacles from the scene once they've moved off screen. We'll add a conditional check to determine if the obstacle has moved off the left side of the screen. We do this by comparing the obstacle's X position to the negative width of its texture. If the obstacle's X position is less than the negative width of the sprite, it means the entire obstacle has moved off screen. At this point, there's no need to keep it in the scene, so we call the queue-free function, which safely removes the obstacle from the scene and frees up memory. Now that our obstacle script is complete, it's time to move back to our main scene where we'll implement a system to spawn these obstacles procedurally. Save the obstacle scene and go to the main scene. Before we continue, let's add a timer node to the main scene. This node will trigger the spawning of obstacles at regular intervals. Set the wait time to 2 seconds, and also enable auto start so the timer starts automatically with our scene. Now let's select the main root node and attach a script called main.gd. Then let's remove the boilerplate code. We start by declaring two variables. The first, obstacle scene, is an exported variable of type packed scene. This allows us to drag and drop our obstacle scene into this variable from the Godot editor. If we save and then select the main node, we'll see there is a field called obstacle scene, where we can drop our obstacle tscn file to reference the obstacle scene. The second variable, obstacle timer, references the timer node in our scene. The timer will control the interval at which obstacles are spawned. Now we'll declare an array called obstacles. This array will store all the obstacle instances that are spawned during the game. By keeping track of these instances, we can easily manage them, whether it's for removing obstacles that are off-screen or for handling interactions between obstacles and the player. Initially, this array is empty, but as obstacles are spawned, they will be added to this list. Next, in the ready function, we connect the timeout signal of our obstacle timer to the spawn obstacle function, which we will define in a bit. This means that every time the timer reaches its timeout, it will trigger the spawning of a new obstacle. Now, let's define the spawn obstacle function, which handles the creation and placement of each new obstacle. We begin by instantiating a new obstacle from the packed obstacle scene. Next, we randomize the direction of the obstacle by setting direction up to a random Boolean value. This is done by generating a random float between 0 and 1 and checking if it's less than 0.5. If true, the obstacle will point upward. If false, it will point downward. We then set the obstacle's initial position. I've set the x-coordinate to 900 for now, placing the obstacle on screen to the right, and the y-coordinate is initialized at 0, but will be adjusted based on the obstacle's internal logic for vertical placement. Once the obstacle is configured, we add it to the scene using addChild. This makes the obstacle visible and active in the game world. Finally, we append the new obstacle instance to the obstacles array. This allows us to keep track of all the obstacles currently in the scene, which will be useful for managing and cleaning up obstacles as the game progresses. Let's save the file and press F5 to play the game and see how it's working. Now that we've set up the procedural spawning of obstacles, it's time to add some interactivity. Specifically, we need to handle what happens when the plane collides with a rock. To do this, let's return to the player and implement the collision detection logic. First, let's add an Area 2D node as a child of the player node. This node will be responsible for detecting collisions with obstacles and triggering the appropriate response. Next, add a collision shape 2D node as a child of the Area 2D node. This shape will define the collision boundaries for the plane. Set the shape to a circle and adjust its size to fit the plane sprite. To help manage what happens when the plane collides with an obstacle, let's add a timer node to the player scene. This timer will be used to control the delay before the player respawns or the game resets after a collision. Now let's save the scene and open up the player script. First, let's drag in references for the Area 2D node and the timer node at the top of the script. Declare a new signal called hitObstacle. This signal is crucial for our game's interaction logic, as it allows the player to notify other parts of the game when a collision with an obstacle has occurred. By emitting this signal, we can easily trigger events like playing a sound effect, displaying a game over screen, or any other response you'd like to implement when the player hits an obstacle. Next, we've introduced a variable called canFlap, which is a Boolean set to true by default. This variable controls whether the player can flap or not. By managing this variable, we can easily enable or disable the player's ability to flap under certain conditions, such as after colliding with an obstacle. In the Ready function, we've added two important signal connections. First, we connect the area entered signal from the Area 2D node to the onArea2D area entered function. This allows us to detect when the plane collides with an obstacle. Second, we connect the timer's timeout signal to a new function called def, which will handle what happens after a brief delay following a collision. Next, we define the onArea2D area entered function, which is triggered when the player collides with an obstacle. Inside this function, we start the timer, disable the player's ability to flap by setting the canFlap Boolean to false, and then remove the Area 2D node by calling queue_free. This effectively stops the player from continuing to interact with the environment until the def sequence is complete. We've also added the def function, which is called when the timer times out. In this function, we emit the hitObstacle signal, which can be connected to other parts of the game to trigger effects such as playing a sound, showing a game over screen, or resetting the game. Finally, we've added a conditional check that combines the canFlap variable with the player's input. This line ensures that the player can only flap if canFlap is true. After the player collides with an obstacle and canFlap is set to false, this condition prevents any further flapping, effectively stopping the player from moving and signaling that a collision has occurred. Let's try this out. Hit F5 to play the main scene, test how this works. You can see when we hit the upper rock, we can no longer flap and we plummet down. To make this more visually interesting, let's add a quick particle effect to show smoke when the plane hits a rock. Go to the player scene and add a CPU particle effect as a child of the root node. In the drawing section, add one of the smoke puff assets as the texture. Next, change the emission shape to a circle and give it a wider radius of around 30 pixels. Now, change the gravity settings to -250 for X so the smoke slowly moves backward and -500 for Y so it moves upwards. Finally, turn off the emitting box so it starts with it off, and then we can turn it on when there is a collision. Let's go back to the code. First, we'll need a reference to our particle effect. Next, we can simply set the smoke particles emitting variable to true, and start the particle emission, visually indicating that the plane has taken a hit. Let's see how that looks in practice. This looks great, so let's continue and work on getting the obstacles to stop spawning when you die, and a retry button to a pop-up. Start by adding a button node to the main scene. This button will serve as the retry button, which the player can click to restart the game after a collision. Adjust the button's text to say retry to make its purpose clear. Position the button near the center of the screen so it's easily accessible when the player needs to restart. Initially, we want the button to be invisible and disabled, so it doesn't interfere with gameplay. To do this, uncheck the visible property in the inspector and set disabled to true. We'll control the button's visibility and interactivity through the script when the player collides with an obstacle. Back in the main script, first add a reference to the button we just made, and the player instance in the scene. In the Ready function, connect the hitObstacle signal from the player to a new function called onPlayerHitObstacle, which will handle the game over logic. Then connected the pressed signal from the button to the onButtonPressed function, allowing the player to restart the game with a single click. The onPlayerHitObstacle function is triggered when the player collides with an obstacle. In this function, we stop the obstacle timer to prevent any more obstacles from spawning. We then make the retry button visible and enable it, allowing the player to restart the game. Finally, the onButtonPressed function handles the retry logic. When the player clicks the retry button, this function reloads the current scene, effectively restarting the game from the beginning. Let's test this out. This is working well. So the last big piece to implement is a score system. To implement our scoring system, the first step is to detect when the player successfully passes an obstacle. We'll do this by emitting a signal from the obstacle script whenever an obstacle moves off screen, indicating that the player has avoided it. We start by declaring a new signal called obstacle passed. This signal will be emitted whenever an obstacle moves past the player, allowing us to track successful avoidance and update the score accordingly. Then in the process function, when we check if the object has moved off screen, we can emit the obstacle passed signal, notifying the game that the player has successfully passed this obstacle. Now it's time to create a visual representation of the score in our main scene. We'll do this by adding a label node to display the player's score. Add a label node to the main scene. Position it near the top center of the screen, and add some sample text like score 0. Now let's jump back in the main script. First, get a reference to the label we just created. Next, add a score variable initialized to 0. This integer will keep track of the player's current score as they progress through the game. In the spawn obstacle function, connect the obstacle passed signal from each spawned obstacle instance to the onObstacle passed function. This connection ensures that whenever an obstacle is successfully passed by the player, the score is updated. Define the onObstacle passed function to handle the score update. When this function is called, increment the score variable by 1 and update the label text to reflect the new score. The label will now display the current score on the screen. Press F5 to see if this is working as expected. We can see the score increase as obstacles move off screen. We need to ensure that when the player collides with an obstacle, not only does the game stop spawning new obstacles, but the existing obstacles also stop contributing to the score. In the onPlayerHitObstacle function, call the DisableObstacleSignals function to prevent any existing obstacles from affecting the score after the player has collided with one. In the DisableObstacleSignals function, loop through each obstacle in the obstacles array. For each obstacle, first, check if it exists and is still a valid instance using isInstanceValid. This ensures that we're only working with obstacles that are still active in the scene. If the obstacle is valid, disconnect its obstacle passed signal from the onObstacle passed function. By doing this, we make sure that once the game over state is triggered, no additional points can be scored. With that finished, all that remains is to add polish to the game. Let's start by adding a parallax scrolling background. On the main scene, add a parallax background, and then add 2 parallax layer nodes as children of the parallax background node. Rename them background and midground respectively. Next, add a sprite 2D node as a child of the background layer, and add the background asset to the texture field. Since the background image is smaller than our viewport, let's set the window size in the project settings to match it. Open project settings, and in the display window page, set the dimensions to 800 by 480. Now reposition the image so that it's in the center of the viewport. Select the background layer. In the motion section, set the scale to 0.25, and in the mirroring section, set the x-axis to 800, which will duplicate the length of the background image. Now add a sprite 2D node as a child of the midground layer, and add the ground grass asset to the texture field. Move the sprite into place at the bottom of the viewport. I set mine in the transform to an x of 400 and a y of 445. Like the background layer, now select the midground layer, and in the motion section, set the scale to 0.5, and in the mirroring section, set the x-axis to 800, which will duplicate the length of the background image. With that set up, let's attach a script to the parallax background to get it to move. Start by declaring a variable called scroll speed, which controls how fast the background layers will scroll. Inside the process function, iterate through each child of the parallax background and retrieve its motion scale and motion offset properties. Check if the child is a parallax layer before applying the scrolling effect. This ensures that only the layers intended for the parallax effect are moved. The motion scale determines how much the layer should move relative to the player's movement, with lower values resulting in slower movement simulating layers that are farther away. Update the motion offset by subtracting the product of scroll speed, delta, and motion scale, x from its x component. This moves each layer to the left, creating the scrolling effect. Finally, apply the updated offset back to the layer's motion offset, making the parallax effect visible in the game. Hit play and let's see if this is working. With that functioning, let's proceed to making a title screen and start game button. Create a new scene with a node 2D as the root. Name it title screen. To maintain visual consistency, we'll reuse the parallax background from our main game scene. Copy the parallax background node from the main scene and paste it into the title screen scene. Next, add a label node to display the game's title. In the inspector, set the text to Tappy Plain to match the theme of our game. To quickly give our title screen a cohesive and polished look, we'll customize the font and size of the title label using theme overrides. Start by selecting the label node in the scene tree. With the node selected, navigate to the inspector panel. Scroll down until you find the theme overrides section. This is where we can apply custom styles to our label, including font and size adjustments. To customize the font, click on the Fonts option under Theme Overrides. Here, we can drag in the font included in the art pack. Right below in Font Styles, we can increase the font size to something like 36. Next, let's go up to the Constant section and make outline size 10 pixels. Finally, add a button node below the title label. In the inspector, set the button text to Start Game. This clearly indicates its purpose and invites the player to begin. For buttons, there are a lot of other style options, but for now we'll just change the font to be consistent. Let's move both the label and the button to both be in the middle of the canvas. While we're at this, let's go back to the main scene and change the font for the score label and the retry button to make everything cohesive. For the score label, I'm also going to increase the size to 36. We'll do the same on the retry button. Now that we've customized the visual aspects of the title screen, let's go back to add functionality to the Start button. Go back to the title screen and add a script to the title screen root node, called titlescreen.gd. Start by declaring an export variable named main_game_scene. This will allow us to drag and drop the main game scene into this variable from the Godot editor. In the ready function, connect the pressed signal from the Start button to a new function called onStartGameButtonPressed. This ensures that when the button is clicked, it triggers the start of the game. Define the onStartGameButtonPressed function, which will be called when the player presses the Start button. Inside this function, use getTreeChangeScene to pack to load the main game scene. Once the script is ready, drag your main scene file into the main game scene field in the inspector. Let's play the title screen scene with F6 to see if this is working. The title screen works, but we can see there's a bug where the game doesn't end when the player leaves the screen. Let's fix this by adding some world boundaries. Go to the main scene and add a new 2D area node. Add a collision shape node as a child, and for the shape select world boundary. The world boundary shape cuts a line across the viewport, where everything below the arrow shape that is visualized is inside the area, which in our case would trigger a collision. Place this boundary just below the bottom of the screen, and duplicate it and flip it upside down, then position it just above the top of the screen. Now let's test this out. We can see our game detects a collision when the plane leaves the screen, triggering a game over. With this fixed, the game is now complete. I hope you enjoyed following along. Please don't forget to like and subscribe for more quick tutorials, and let me know if you would like shorter or longer tutorial content in the comments.